AM radio has seen a resurgence on the amateur radio bands in recent years. It started out as being the only form of voice communication up until the late 1950s. In the early 1960s, single sideband took over and was king up until kind of now, where people are getting interested in the mode again, mainly due to the audio quality that AM offers as compared to single sideband. You can get voice, broadcast quality audio out of your transmitter if you design it properly as compared to single sideband. There's also the nostalgia factor. Some people like restoring old transmitters and putting them on the air using vacuum tube technology. And some people even take from AM broadcast transmitters, convert them to amateur use, and use these big monstrosities in their ham radio shacks. All sorts of different flavors of transmitters out there. What I'm going to do is do a series of videos on building a Class E solid state AM transmitter. Now, I don't pretend to be the guru on Class E technology. That title goes to Steve, WA1QIX in Massachusetts. He has his own website which gives instructions, very detailed instructions on how to build one of these transmitters. High power, high fidelity audio, highly efficient, over 90% efficient, so you're not using lots of power to generate 400 watts carrier. The benefit to Class C as well is that it's solid state. There are no high voltages or dangerous voltages to deal with, so there's a safety factor there as well. So these series of videos are going to chronicle my progress on building these. Now, I've built several Class E transmitters before. I've built a single MOSFET 40-meter transmitter. My next step was an 8 MOSFET Class E transmitter, which was 400 watts carrier with voice peaks in excess of 1500 watts, the legal limit for amateur radio. I followed that up with another few just toy projects, and I finished it off with a 24 MOSFET 75-meter transmitter. It was quite the monstrosity. Now, those are all gone now. I usually scrap what I build for some stupid reason, but now I'm living in California and I'm going to build another one. This one will be an 8 MOSFET 75-meter transmitter. So there are lots of videos on YouTube for restoring old transmitters and doing this and that and the other. I cannot find one which details how to build a Class E transmitter, so here we go. Now, there are several ways to do this, so don't try to cookie cutter my way of doing it. Building radios is as much a science as it is an art. The best way to build one of these transmitters is to understand the big picture of how you get there and then do your own flavor. So the best way to do that is through experimentation, through reading, through research. It sounds complicated, but it really isn't. So the building blocks for this transmitter is right here. This is also one of Steve's designs, but I've modified it. I've actually simplified it for what I wanted to do. This takes an input from a VFO, a variable frequency oscillator, and it takes that sine wave from the oscillator and converts it into a two-stage output, two square wave outputs that are 180 degrees out of phase. You can adjust the duty cycle of each phase with these two potentiometers right here. Now, for Class E transmitters, when you drive the gates of the MOSFETs, you want to target around 40% duty cycle, which can be adjusted with these potentiometers. So on Steve's design, if you go to his website, it's www.classeradio.org. If you go to his website, you're going to see this schematic on there for a VFO. Now, he designed his for use on 160 and 75 meters. I've simplified it because I only want 75 meters. So this first chip right here is a JK flip-flop. What that does is it takes a sine wave from the VFO into the clock input and sends out an output that toggles on the clock pulse, on the negative going clock pulse, with two outputs, the JK flip-flop. That then goes to two logics, what's the word I'm looking for? A NAND chip and a can't think of the isolating chip for the logic to get the square waves at the reduced duty cycle. So you're not sending a 50% duty cycle into the gates. You can adjust that down with his design to less than 50. So like I say, you're wanting in for 40. It's going to sit in this box. So it goes in here just like that. So the input is input for the VFO. Keying, when you want to key the transmitter, 12 volts goes in here. The two 180 degree output digital square waves come out here. And there's an output for VFO if you want to monitor the frequency of the VFO. Now, one important thing, the purpose of the JK flip-flop is to divide the frequency by 2. So you have your VFO operating on a frequency that is twice the operating frequency. The reason for that is I'm showing my SDR receiver right here. I'll be pairing this SDR play with this transmitter. During receive, if you don't have the frequency, if you have your VFO set for the operating frequency, you're going to see your VFO carrier right here, and it's going to interfere with your reception. So if you double the frequency, you're way off in over 7 megahertz. You're never going to see the carrier. And so there you go. So this will sit on the side. Here's the, let's go over the overall design here. This is just, these are empty boxes right now. I just have the face plates on here. But this will be the power supply. I'll have, it'll be on, and this will be a switch for 22 volts or 44 volts on the drains of the MOSFETs. And I got an old antique meter there just for looks. Well, it'll be functional, but I like the old antique look style. And so when you want to tune the transmitter, do it at reduced voltage so you don't damage anything. And then operating, you put it up to full power. This section right here, there won't be much on it, but on the inside will be the analog modulator. That will take audio from a solid state audio amplifier, which is sitting on my desk over here. This old Radio Shack Beastie. That's just a regular public address amplifier. The 8 ohm output of this will be coupled over here into this analog modulator, Class A modulator, and the 44 volts from here will go into here, coupled with the PA amp, and to drive the drain of the MOSFETs. That's where you get your voice modulation. And these two meters right here will monitor both phases of the drain currents. So this VFO is going to sit right on the side here. I haven't mounted it yet, obviously, because I haven't done this. But also incorporated into this transmitter, this is the actual VFO. Got it off of eBay. It's a regular old Chinese DDS VFO. Set it for twice the frequency, put it into the duty cycle adjuster, and you're off and running. This 12 volt power supply will be supplying a little over 12 volts to the IXDD drain bus. The IXDD drain bus drives the gates of the MOSFETs. Though that will be powered all the time, this will be keyed on and off to drive, to determine, for receive. There will be no drive to the IXDD bus. During transmit, this turns on. Another important factor to consider with Class C transmitters is everything needs to be sequenced. You have to build, for example, I'll just show you what I've done. I'm not going to go on the air, but this will key the relay so you can hear it. This is my transmit receive switch. Now listen when I go to transmit. Hear all those relays clicking, and they go off when I receive. So what those are is sequencing events in proper order. So with a Class C transmitter, what you want to do is key the antenna relay for transmit to receive, then key your IXDD bus drive, and then key drain voltage to the MOSFETs. As a fourth step, you want to tie in your analog modulator. If you're using pulse width modulation, it's a different story, but we're not going to go into that because I'm not going to do it that way. And when you go from transmit to receive, the order has to be reversed. So that has to go from PA amplifier cutout, MOSFET drain bus cutout, then the IXDD drain bus cutout, and antenna relay over to the receive, just like you heard. Now there's several ways to do that. I have a YouTube video on just a simple mechanical sequencer. You can research that and find it. I built this. It's under the desk, but this logic circuit that does it electronically for me. So all I have to do is key the switch. It sounds like a lot of stuff. I know it does, but really, this is the hardest thing to do with a Class C transmitter. Once you build this duty cycle adjuster, the rest is just drilling and blasting, essentially. Now, there are tricks to the trade. There's component placement, there's all that sorts of things. It's not like designing with a Raspberry Pi. With a Raspberry Pi, it's like a computer. You just put the wires in, the logic takes over. Building radios is, it takes a certain skill set, because you're also not dealing with just electron flow. You're dealing with waves and fields that interact with each other. You can't see them, obviously, but they all interchange. They all have an effect on each other. So like this tuner here, if you look at this tuner, this antenna tuner I built is a Pi antenna tuner. All the components are 90 degrees out of phase, so 90 degrees out of mechanical placement, so they don't interact with each other. Well, Class C is no different. Your output network is very important as to where you place your loading capacitor, your tuning capacitor, your tuning inductor, all these things. So this may sound overwhelming if you want to get into Class C, and I'm sure it is. But if you look at Steve's website, look at other examples of what people have done, start experimenting on your own with a single MOSFET, just play with it and have fun with it. So this is the first step. In the next video, I'm going to be testing this duty cycle adjuster so you can see what the waveforms do on the oscilloscope and kind of see where you want to go with this thing. So that'll be the next step. So for now, thank you very much. My name is John Rhines, KA1TDQ in San Marcos, California. Have a great day.